Good morning, students. We are meeting again for the third and the penultimate part of your first lesson in chemistry book, Chemical Reaction and Equations. Well, let us first recap a little bit what we had learned on the previous lesson. In the previous lesson, I discussed mainly about how to balance an unbalanced and skeletal equation, how to write a proper balanced chemical equation that satisfies the law of conservation of mass. Writing a proper balanced equation is when you start really to understand the essence of chemistry. So it's a very important lesson. And also in the upper classes you will learn how to balance the ionic equation so that the net charge is also balanced. Let us stress the importance of the proper way of writing an equation. Please look back to the steps that we must follow to balance an equation once more, just for a second. What is a chemical equation? The shorthand method of representing a chemical reaction in terms of symbols and formulae of the different reactants and products is called a chemical equation. A chemical equation may be of two types: unbalanced or skeletal equation and a balanced chemical equation. An equation in which the number of atoms of different elements, one or more, is not equal on the two sides of the equation is called an unbalanced or skeletal equation. Vice versa, an equation in which the numbers of atoms of each element, numbers of atoms of each element on the two sides of the equation. Remember this point, numbers of atoms of each element on the two sides of the equation are equal, is called a balanced chemical equation. Simple steps: the symbols and formulae of the reactants are written on the left hand side, LHS, with plus sign between them. The symbols and formulae of the products are written on the right hand side, RHS, with plus sign between them, and an arrow sign is put between the reactants and the products, pointing from left hand side to right hand side. Now this is most important. You must methodically follow the steps to balance a chemical equation. First, write the word equation. Second, convert it into skeletal unbalanced chemical equation. Enclose the formulae, each formulae, in separate boxes. The boxes will work like brackets. List the number of atoms of different elements on left hand side and right hand side. Mind you, the number of atoms must be balanced. Select the biggest formula to start the balancing. It's a convention, not a rule. Number 6, start balancing different elements. And finally, of course, check the correctness of the balanced equation. Right? Now, you now remember the steps I told you to methodically follow in balancing. I had also given you a lot of exercises, simple exercises, to balance and practice balancing equation. But on doing so, I also remarked that there are some precautions and some don't and some things you have to remember especially. You cannot change the subscript. You can only use positive integers as the coefficient in the final equation, etc. Plus, these are very important. Please look at them once more. We must remember these points very carefully. Number one, to make the number of atoms of any element, atoms of any elements, not molecules. To make the number of atoms of any element equal on both sides of the equation, we cannot change the subscripts of the formula. This is very important. Number two, what we can do, we can only change the coefficient before a formula. So, whenever you are changing a coefficient, that is the third point, the coefficient before a formula multiplies every atom of that formula by that number. Please remember these 3 points very carefully and let me discuss them further. You see, you cannot stress these points enough. Most important points. The subscript, I remind you, denotes the atomicity. And the coefficient must be positive integers. How these problems crop up, just to show that, and also to give you a recap step by step how to balance an equation. I am showing you a problem. This is hexane. What is hexane? Hexane is a carbon compound, saturated carbon compound. Ethane, methane, propane, butane. You will learn about them a little later in this year itself. Hexane burning with oxygen, natural oxygen occurring in air, producing carbon dioxide and water. Look at the skeletal form. Hexane is C6H40. Oxygen, since it is naturally occurring, it must be O2 because oxygen cannot move separately as atom in the free state. It must be molecule. So 2 atoms of oxygen, but mind you, it is actually 1 molecule. You should remember the difference when we write 2O. Actually, it is 2 atoms of oxygen separate oxygen. But if we write O2, that is 1 molecule of oxygen. There are 2 atoms again, but they are connected to each other. This is the kind of problem we will face in this equation. You see, CO2 and H2O. Here is 1 atom of oxygen. There is 1 molecule of oxygen. Keep this in mind and let us go to the step first. What happens is, look, we will first box each item. Then the next step, you remember, we tabulate. Our substances taking part on the left hand side, right hand side. Mind you, we count the atoms here and balance the atoms, not the molecules. Balance the atoms of the reactant and atoms of the products. Carbon 6 on this side, 1 on that side. Hydrogen 14 and on that side 2. Oxygen 2 atoms, 1 molecule but 2 atoms on this side, and 2 and 1, 3 on that side. Let's start balance. We'll start as a convention with the largest number of atoms, that is 14 hydrogen. Let's multiply it with 7. Now what happens is that there is only 1 product with hydrogen, so we must multiply this molecule of water with 7. So the number of oxygen also changes, but we will come to that later. Let us first balance the second largest number of atoms, carbon. Let's multiply it with 6. So only compound with carbon on product side, that is carbon dioxide, we must multiply it with 6. What happens? Carbon is balanced. Hydrogen is balanced. How many oxygen atoms are now on that side? 6 into 2, 12 and 7. So now on the product side we have 19 oxygen atoms. But on we cannot just change it into 2 into 19 on this side. Because you remember here the 2 oxygen atoms are actually in the molecule form. So to have 19 atoms, how many molecules we must be taking in the reactant site? You see, if 2 atoms of oxygen equal to 1 molecule of oxygen. So 1 atom of oxygen equal to half molecule of oxygen. That cannot be. How can there be a half molecule? Half atom. That is not possible. So 19 atoms of oxygen equal to 19 by 2 molecules of oxygen. Now you get the problem. We actually have to, here we have to multiply this side by 19 by 2 to have the exact number of molecules on the reactant side, so that the balancing equation gives us the same number of atoms of oxygen on the both sides. If we have 19 by 2, that means nine and a half molecules of oxygen. Only then can we assure that both sides has 19 atoms. But let's write this now. C6H14 plus 19 by 2 O2 or 9 and half O2 molecule becomes 6 CO2 plus 7 H2. Only then it will be balanced. But again the problem remains. We cannot have half molecule. In fact, we have to have only positive integers in the final balanced equation. So what to do is very simple. We multiply both sides of the equation with 2. What does it look like now? 2 into C6H14 plus 2 into 19 by 2 O2 leads to 2 into 6 CO2 plus 2 into 7 H2O. What happens is 2 molecules of hexane, 2 molecules of hexane reacts with 19 molecules of oxygen, that is 38 atoms, produces 12 molecules of carbon dioxide and 14 molecules of water. You understand how interesting problems crop up, and unless you keep all the precautions and steps and do them methodically, learning to balance the equation is very funny, but it's also not an easy task, right? So you have followed this problem. Let us move forward to the actual lesson we are going to learn today. How many kinds of chemical reaction happen? We have listed 7 reactions in total that you should learn at this stage. I will give the definition one by one. We need another period also. Today, first we learn 4 kinds of reactions, but you have a look at the list of reactions that you must learn today. Memorize this very carefully. Depending upon the nature of reaction, chemical reactions have been broadly classified into 7 types. Combination reactions, decomposition reactions, precipitation reactions, neutralization reactions, which we also call acid-base reactions, displacement reactions, double displacement reactions, and reduction-oxidation reactions, which we also call redox reactions. Please memorize this. You see, these are the kinds of reaction you have to learn at your stage of learning now you are in. It is not that all these reactions are all separate from each other. Most of the time 1 or 2 reactions happen simultaneously. The features can be in the same reaction. But for learning's sake, easy learning, we must learn them separately. What are the special features? First, we have taken combination reaction. When I give you the definition, apparently it will seem that combination reaction is no different from the definition we learned about chemical reaction itself. What is chemical reaction? Such a chemical change where 2 or more substances combine to produce new substances with new properties. On the face of it, combination reaction seems to be following the same definition, but with a vital difference. Mark it. What is a combination reaction? Combination reaction is such a reaction in which 2 or more than 2 elements or compounds, it may be elements plus elements, compound, elements plus compound, compound, compound plus compound, compound. But 2 or more elements and compounds combine to produce a single compound. That is the speciality of combination reaction. It must produce a single compound, single product. Only that kind of reactions we call combination reaction. For example, it can be of 3 types. Let's say it may be element plus element, and the product of course is a compound. Let me give you some basic examples. Like you see, if we burn magnesium in air, that is in the presence of oxygen, is produced magnesium oxide, which is a compound. Element plus element produces compound. Suppose we burn carbon in oxygen, element and element, and produce carbon dioxide gas. Now the second kind of combination reaction, the product is always a single compound. Element plus compound and producing a single compound. For example, let us say we take sulfide dioxide gas and combine it with oxygen gas. You see what is produced? A new gas, sulfur trioxide compound plus element compound. Another example we may give, very common example. We take carbon monoxide gas and mix it with oxygen. It will produce carbon dioxide gas. Carbon monoxide plus oxygen. Third kind of combination reaction, it may be like this. Compound plus compound produces another compound. Single. That is the speciality of combination reaction. If we combine, say, ammonia gas, NaC we had learned previously that it is ammonia gas, and react it with aqueous solution of H2SO4, that is actually diluted sulfuric acid. What will happen? It will result in ammonium sulfate. Okay, look at this. Mind you, this formula I am writing here, ammonium sulfate. Sometimes they may be unbalanced. If you are serious, you can go through each of these equations and check if they are balanced or not. And if they are left unbalanced here, you try to balance them yourself. Another common example of compound plus compound is calcium oxide. Calcium oxide, you know, is the quicklime. When you mix it with carbon dioxide gas, it will produce calcium carbonate. These are some of the examples of combination reaction. Let us look at a slide with the definition and a few more examples of this work.
Those reactions in which two or more elements or compounds combine together to form a single compound. This is important to remember. Only those reactions are called combination reactions. Product must be single. It may be of three types: elements plus elements. Here you see that ferrum, that is iron, reacts with sulfur. When it is heated, it produces iron 2 sulfide. Iron 2 sulfide, ferrous sulfide, because its valence is 2. Second example I have given of element plus compound, in which nitric oxide in the gaseous form nitric oxide in the gaseous form reacts with oxygen also in the gaseous form to produce nitrogen dioxide. Here the reaction is between an element and a compound. Third reaction I have given an example of is compound plus compound, NH3, that is the ammonia gas, and hydrogen chloride. When they mix, they produce ammonium chloride.
Decomposition reaction is technically the opposite of combination reaction. In combination reaction, a single compound is formed, and in decomposition reaction, a single compound is broken apart to form two or more simpler substances. Simpler in the sense that they are simple in, more simple in chemical construction than the reactant compound. You see, such decomposition, breaking down, it's not so easy as the combination, because in combination, if two or more reactive substances come together, they almost on their own volition react. But a single compound, it's not easy to break it down because there is a strong force of cohesion between the particles of that substance. So we need to supply some extra energy to make this decomposition happen. Decomposition reaction needs some input of energy. It may be heat energy. If decomposition happens because of extra heat energy, thermal energy, we call that thermal decomposition or thermolysis. We can also put that extra energy. We'll see that how water is broken down to produce hydrogen and oxygen gas commercially in the plants. That kind of electric decomposition where electricity puts the extra energy, electrolysis. And also light, in particular in sunlight. It happens because you see that sunlight decompose the dead bodies, dead organisms. This kind of decomposition is called photodecomposition or photolysis. Let me give you some examples one by one through slides as well as on the board. Suppose we are taking copper sulfate pentahydrate. This is called pentahydrate because it has 5 molecules of water crystallization. Actually, these copper sulfate pentahydrate crystals. What happens that we heat it to 100 degrees Celsius and it decomposes to form you see that it's a new crystal. It is now copper sulfate monohydrate. If we go on heating further and at a higher temperature, say we heat it to 230 degree to 250 degree Celsius. Now, the last molecule of water of crystallization will go and vaporize. And now it is anhydrous copper sulfate. This is where extra heat energy decomposes a complex substance into simpler substance. I can give you another example. is also in the crystal form. Heptide, ferrous sulfate, it's hydrated crystals. If we heat it will produce you see, that is water, water is liquid, and this is anhydrous, hydrated ferrous sulfate, and now it is anhydrous ferrous sulfate and water, two simpler substance than the original reactant. Let's look at it in detail in the slide.
The reactions in which a single compound, just the opposite of combination reaction, a single compound as reactant breaks down to give two or more simpler substances. Product must be simpler in construction than the reactant. Such reactions are called decomposition reactions. It can be of three types because it needs some energy input to make it happen, to make the bond of force of attraction between the particles of the reactant substance to break down. This may be of three types depending on the stimulus. Thermal decomposition reactions. It needs heat energy to make it happen. Electrolytic decomposition reactions or electrolysis, of course it needs electricity. And photo decomposition reactions, photolysis, it needs light as stimulus. You see, all decomposition reactions, they absorb energy. That's why all decomposition reactions are endothermic reactions. Now, here we give an example in the laboratory. Look at it closely. We have taken powdered lead nitrate in a dry test tube and heated it over the flame. You see, brown fumes of lead nitrate becomes brown fumes of nitrogen dioxide, and a yellow residue of lead oxide as crystal is left behind the test tube. It is a decomposition reaction by heat. 2PbNO3 solid, that is lead nitrate, that sign in the middle is heat, and it creates lead oxide, nitrogen dioxide and oxygen gas.
Now let us come to the second kind of decomposition reaction, electrolytic decomposition reaction, where we supply electric energy to break up a compound. The most common examples is the breaking up of water into hydrogen and oxygen gas. That you will see through a slide I have prepared with a detailed experiment. Let us give you some extra examples. Suppose we take sodium chloride in its molten means, which is not totally melted and not solid, in a halfway stage, and we supply electric current through it. We do electrolysis. What happens is that sodium is separated and chlorine as a gas, it goes away. This is one way of purifying sodium. Same way, from an aluminium ore, you know, you have read in the previous class what is an ore. Aluminum is gotten for the aluminum oxide ore, that is alumina, we call it aluminum. Same. It's also in the molten stage. Remember, we call it, the ore is alumina. And we give electrolysis treatment to this aluminum. The result will be pure aluminum metal, and the oxygen will go up as gas. Now look at a slide of the most common way to get hydrogen and oxygen gases in a plant on a commercial scale. Electrolysis of water.
Look at the picture very carefully. The equation is very simple. Two molecules of water, we supply electric energy through it and it breaks down into hydrogen and oxygen gases. This is how it is produced. These gases are produced commercially on a large scale. And here the setup, the machine that is being used, it is called a voltmeter. It's an apparatus for carrying out the electrolysis. If you note that there are two anode and cathode, two terminal connected with a battery, and these are the carbon cathode and carbon anode. Two graduated, calibrated test tubes are put on it, and the water mixed with a few drops of sulfuric acid, H2SO4, to help it ionize faster. Two gases evolve, and you see on the negative terminal, that is the cathode, the gas there is hydrogen because it burns itself. And at the positive terminal, that is the anode, oxygen gas is involved. It helps burn. So you understand this way is another simple example of decomposition reaction by electricity. Hydrogen, since it forms a cation, it comes to the negative terminal, that is cathode. And oxygen, since it has formed an anion, it has come to the positive terminal. That
now the last one, the photo decomposition reaction, where usually sunlight affects the reaction, decomposition reaction. We have also prepared an experimental slide on it, but let me give you a simple examples. Like we take silver bromide. It is silver bromide, which is solid. We supply, keep it in exposed to sunlight. The result is that silver and bromine, silver and the bromine, they are separated. Now, you see, this is an example of what a photolytic decomposition reaction is. And it is a little uncommon, hydrogen iodide. We have to supply not only light but also ultraviolet light, ultraviolet rays. Exposed hydrogen iodide exposed to ultraviolet ray will separate it into hydrogen and iodine separated. Let's look at a slide of another common experiment with this photolysis, and then we will go to the next part of the reaction.
here silver chloride crystals, which are white in color, they, after being exposed to the sunlight, produces silver, which is gray in color, and Cl2, that is chlorine, it is forming a gas. So this is an example of photo-decomposition reactions or photolysis.
Precipitation reaction. Precipitation reaction, you also should know what is a precipitate, okay? Let's look at the definition first. Precipitation reaction occurs when the aqueous solutions, both of the compounds must be in their aqueous solution in liquid form. When aqueous solutions of two or more compounds, they mix up, and on mixing, an insoluble compound comes out as solid, separates out as solid, and drops at the bottom. This separating solid is called the precipitate, and this reaction is called precipitation reaction. What happens? Two solutions are mixed, and as a result, whatever else happens, one substance comes out, separates out itself from that aqueous solution and forms as a solid. It's called precipitate, and the reaction is called precipitation reaction. Let me give you one example of silver nitrate solution and sodium chloride solution. Both are in aqueous solutions. Let's see. You will see that if anywhere you have any doubt about whether the formulas are balanced, I am suggesting you look up if they are balanced. Stop the video and write them down. See, check if they are balanced. If not, do it. Right? It is silver nitrate in its aqueous solution. We are mixing this solution with sodium chloride, common salt solution. And the result becomes, you see, those are both are in liquid form. Result is that one portion of the reactants is remaining as aqueous solution. That is the you will balance the yourself. This sodium nitrate remains aqueous, but silver chloride, it comes up as solid, and this is what we call precipitate. It drops in the bottom. This kind of reaction is precipitation reaction. Two solutions on mixing produces at least one solid precipitate. There is another way of looking at this precipitation reaction. Let's also learn it. Sometimes when in an aqueous solution, through an aqueous solution, we don't mix another solution, but we pass a certain gas. A gas goes through a certain solution. Liquid mixes with gas, and one solid precipitate forms. We also call that precipitation reaction. A very common example. Calcium hydroxide. You know, it's in its aqueous solution. When carbon dioxide gas is passed through this lime solution, tuna solution, what forms is that? H2O water is separated, it's in liquid form. But calcium carbonate becomes solidified and hangs inside the water as a suspension. You know what was suspension? suspension is showing some solid, insoluble solid, hangs inside the liquid. This calcium carbonate does not precipitate at the bottom, but it is also precipitate. This is also an example of precipitation reaction. Now let's
look at it very carefully, because there are two ways of looking at a precipitation reaction. Those reactions in which aqueous solutions of two compounds on mixing react to form an insoluble compound which separates out as a solid. The solid portion is called precipitate, and such an reaction is called precipitation reaction. But it is another way of describing a precipitation reaction, that is, an insoluble compound is formed when a gas is passed through the solution of a compound. Gas passing through aqueous solution of another compound and forms precipitates. That is also another type of precipitation reaction. Here you see that barium chloride in its aqueous solution and sodium sulfate also aqueous solution. These two mix and react. What happens is barium sulfate, an insoluble solid, precipitate. It drops to the bottom of the test tube, and NaCl, sodium chloride, it remains in the aqueous solution. This is an example of precipitation reaction.
Neutralization reaction, commonly known as acid-base reaction. We will learn in detail about it in our next chapter, acid, base and salts. So I am not going into detail here. Just showing it that when an acid solution is mixed with a base solution, a salt is produced with water. This is called neutralization reaction, because the properties of acid and properties of base, which are opposite to each other, when they come together, they neutralize each other and form a salt with defined properties with water. This is the basis. We will go into detail in the actual period on acid, bases and salts. Let's give you some examples, common examples. Like say, sodium hydroxide, aqueous form, is mixed up with say hydrochloric acid. It is also diluted. They together will form sodium chloride. It is aqueous form, that is H2O. What? In the same way, if we had mixed this one and mixed it with, say, H2SO form, that is sulfuric acid, what would have happened is that a new salt was formed, that is sodium sulfate and water. If we had, say, potassium hydroxide, which is also a base, this is base. Look at it, this hydroxide form, it is base, you remember from here. And where is hydrogen compound, in an acid, one hydrogen must be there and one hydroxide ion must be there in the base. So these are the base, these are the acids. But potassium hydroxide of base mixed up with, say, hydrochloric acid. You can understand what will happen. It will happen into potassium chloride and what? I give you the definition and a few more examples in the slide. Please look at the slide.
A reaction in which an acid reacts with a base to form salt and water is called neutralization reaction, because acid and base neutralize each other to form that salt. It is also known as acid-base reaction. Here, look at the two examples. COOH2, it is oxalic acid. Commonly, it is found in that, like tomato, you can find it, oxalic acid in that. It mixes with sodium hydroxide, a base, to form the salt sodium oxalate plus water. In the second example, you are seeing that sodium hydroxide base is mixed up with CH3COOH, which is acetic acid. In common day, we find it in vinegar, to form the sodium acetate salt and water.
We'll stop here with discussing the different kinds of reactions because it's better to go slow but steady. I have kept three major kinds of reactions: displacement reaction, double displacement reactions, and the redox reaction, reduction-oxidation reaction for the next and the last period. But before finishing today, I suggest that you look up a little on your own. I will give you some slides also on this reactivity series of metals. This will be important in the next phase, in the displacement reactions. What is a reactivity series of metals? Actually, we make a vertical column. We arrange the metals vertically. The most reactive metal on the top, and then in decreasing order of its reactivity. And this column is called an arrangement of metals in order of their decreasing reactivity, vertically, top to bottom. Such a series is called a reactivity series of metals. Relative reactivity series of metals, activity series of metals. You see that in very common metals. You don't need to learn all the metals. I will show you a way of that also by going through the periodic table in the slide. But here I say potassium is on the top because potassium is the most reactive. Next, sodium, barium. You have to learn the most common, not very. These are the most reactive and common metals. You go through the next slides and learn, be prepared a little for the next class. That will help you better. Look at the slides.
Although I told you that reactivity, you need it more, the reactivity series of metals. Actually, metals and non-metals, in fact, all the elements can be arranged in a reactivity series in order of their reactivity. So, we give the definition of both metals and non-metals here, though you need more about metals in this class. The arrangement of metals or non-metals in a vertical column in order of their decreasing reactivity from top to bottom is called the reactivity series or activity series of metals or non-metals. In fact, the elements, if you ask me like that, relative reactivity of metals in relation to each other or non-metals helps us understand which element will replace which in a displacement reaction, which we will discuss tomorrow, next class. Look at the series. Here you see why I am telling that actually it is a reactivity series of both metals and non-metals, because you have seen in red letters carbon and hydrogen here, which we place among this reactivity series among the metals to show which one is more reactive than the other so far elements are concerned. Now, there is a general rule about knowing which element is more reactive than other, which metal, which non-metal. That you have to practice in the upper classes. In the next periods we also will discuss about it. But let's have a basic look at the periodic table. You see, periodic table, if you ask about the metals, periodic tables have columns and rows. Vertical columns, these are called the groups, and horizontal rows, they are called the periods. The reactivity of metals, remember it carefully, reactivity of metals increases as we go down a vertical column, and reactivity of metal decreases as we go from left to right along a period. So, if you look at any metal, which metal will replace which, and you are given names of two metals, you check their position, which one is upper, then it is less reactive, and which one is on the left side, then it is more reactive in that way. Now look at the non-metals also. Non-metals does the opposite. Non-metals reactivity decreases as we go right to left, and reactivity increases as we go from down to upwards. These ones you will practice. If you just go on practicing from now on, it will be easier. And remember the last column, it is the noble gases column. It does not react at all, right?
So students, this is the third part of this chapter. We will have one more period. Do take it very seriously. I have given you step by step introduction to how to balance a reaction, what kind of reactions are there. We have discussed with lots of examples. Go through the example, practice writing those equations, and if they are not balanced in your eyes, try to balance them. And also learn the metal reactivity series as much as possible. Look at, put a periodic table. If you don't have one, buy a big periodic table and put it on your wall or where you study, so that it is always before your eyes. It is very important. Do these things at home. Be prepared for the next life, for scientific studies, research studies. I expect that apart from doing that exercises I provide you, we will meet in the next video. Till then, thank you.